Welcome back, and I emphasize back, welcome back, because if you're looking at this 6A, this is part 2. We covered the first page of this yesterday, where we talked about sinusoids and inverse functions. So if you're looking for more information on that, that's on the video before this. We went through examples of finding arc lengths, and we went through some inverse functions. I'm going to talk about this just a little bit. When we talked about inverse trig functions, if a problem starts with an inverse trig function, there will be exactly one answer. Now this says, I would probably write this as sine inverse of 1/2, but this says what angle measure gives us a sine ratio of 1/2? And we worked through that. Now I'm going to go through, we did these on the previous video, but I'm going to add C here. I'm going to say cosine inverse of -1/2. So this is what angle measure gives me a cosine ratio. Our cosine ratio in SOHCAHTOA land is adjacent, this is just any old angle, is our adjacent x on our hypotenuse r. So we want to know when x on r is in ratio -1 to 2. And that can only happen when x is negative, because r is always positive. Therefore, I'm going to look to the left when x is negative. Now this I recognize, this is a 30, 60, 90 right triangle, a 1, 2, root 3, but x is the short side, so I'm only going to go over a little bit and down further. Like -1, root 3, 2, or -1, negative root 3 here, positive root 3, 2. So yesterday I said we choose whichever of the two angles, because there's only one answer, is closest to 0. Well, this is a tie, and cosine will always be a tie, cosine inverse. So if it's a tie, the rule is we choose the positive value. So this is 60 degrees short of 180, or 2/3 pi. Okay, just wanted to throw that one out there just to mention that cosine will be a tie. We always go in a positive direction with cosine. Okay, now we are to graph sine and cosecant, and if you're taking AP Calculus right now, we should probably have a pretty good feel for why we're graphing sine and cosecant together on a given interval. So we're going to go from -pi to pi. So -pi here to pi there. I'm just going to put pi on 2's in there. You may know why already. Now, I always use just the plain old, now I know we're graphing plain old sine, but if I was graphing 2 times sine of x on 2 minus pi on 4, I would still come back to my plain old sine graph and talk about the defining values. See if I can get those 5 points shifted, transferred around, moved up, down, right, left. If I can get all of those, then I can fill in the curve pretty effectively. So I do want to show this. Others, rather than memorizing this graph and knowing 0, 0, pi on 2, 0, pi, 0, 3/2 pi, -1, did I say pi on 2, 0, pi on 2, 1, pi 0, 3/2 pi, -1, and 2 pi 0, do this with a unit circle. If this is a unit circle, then this point right here is to the right 1 up 0. Going around our circle, we get to this point where we're to the right 0 up 1. Continuing around to this point, we're left 1 up 0. And to this point, we're right 0 down 1. And here's the key. Sine of these angles, 0, is always the y-coordinate. So sine of 0 is 0. Here it is. Sine of pi on 2 is 1. There it is. Sine of 180 degrees, or pi, is 0. It's always the y values. And sine of 270 degrees, or 3/2 pi, is -1. Whereas cosine, blue, I think we can distinguish that, is always the x values. Cosine of 0 degrees or 0 radians is 1. Cosine of pi on 2 is 0. Cosine of pi, -1. And cosine of 3/2 pi, back to 0. So I don't care which of those you use, but you're going to see me use this a lot. But in this case, it's plain old sine. So plain old sine has defining values at here, at here, at here, and we're only supposed to go to pi, so I'm going to build back here and there. I didn't interval very well. I graph my trig functions by going to my peaks and coming straight, flat out, and then curving down. I don't want it to look like a V up here. It comes out of there flat. And then I go to my valleys, out flat, and make the curve fit. And for me, that just gives a better shape to the curve. So there is our sine graph. Let's go ahead and put our cosecant graph on here. And we should know that cosecant is the reciprocal of sine. So I look at all of my center line points. And the reciprocal of my center line points, zeros, is like 0 on 1 is 1 on 0. It's undefined. So all of my center line points are asymptotes. Now let's look at this point right here. Up 1, the reciprocal of 1 is 1. So that's a point on my new curve. Somewhere along the line, from pi on 2 back to 0, I hit a half on the y value. It's actually at pi on 6. The reciprocal of pi on 6 is 2. And likewise, at 5/6 pi, I hit a half. I'm up here at 2. And that gives us our shape of our cosecant graph. Likewise, reciprocal of -1 is -1. Reciprocal of -1/2 is -2. So there's on the interval from -pi to pi, the blue being our cosecant graph. Oh, I was actually right over there. The blue being our cosecant graph and the black being our sine graph. Okay, and now we're going to start talking about transformations of these graphs. Now, we can determine, if we didn't need a graph, we could determine the amplitude, the period, the horizontal shift, and the vertical shift of this. It's all about a cosine of bx plus c plus d. The amplitude, how nice, is strictly the a value, but it's always positive. Our amplitude here is absolute value of 2, 2. And what the amplitude is how far, how low we go down from sea level. For instance, on this sine curve, regular old sine curve, it's not the distance from the bottom to the top. It's from sea level to the top. And that's a distance of 1. In this case, that distance is going to be 2. Our period, to find the period, you take b, our multiplier, and put that under cosine's period. Cosine's period is 2 pi. So in this case, we would have 2 pi divided by what's being multiplied by x here, 1/3. That's 2 pi times 3, or 6 pi. Now, I really like thinking of it this way. I would say that's an x. I would say everything looks like cosine except it's twice as tall, and this is a pre-function. It affects x. Everything happens 1/3 as fast. But another way of saying 1/3 as fast is to say 3 times as slow. So if the normal period is 2 pi, now everything happens 3 times as slow. It's going to take 6 pi to repeat. Horizontal shift. We get the horizontal shift by finding what I refer to as the MIVOX. And we get the MIVOX by setting the argument bx plus c equal to 0. So the horizontal shift is -c on b. But in this case, there is no horizontal shift because I don't have a plus or minus number in here. So my c value is actually 0. So our horizontal shift is 0. And our vertical shift is always d. And I have no d here, so there is no vertical shift. Okay? So we could use that information and draw our graph, but I'm a big rubber stamp fan, and I'm going to go through this and show you all of this is revealed in the rubber stamp process. So what would we do if we were graphing this? We would choose a value for x, we would divide 3, we would take the cosine, and then we would multiply by 2. Now, I'm going to tell you only need, up until this point, we've been doing 5 values in our stamp. You only really need 2 if you know what the graph of cosine looks like. The graph of plain old cosine we know looks like this. It starts at a peak. Okay, the key here in this stamp, I don't want to choose values for x. I want to choose values for x after I divide by 3, and I want those to be 0, pi on 2, and in the past we'd go to pi and 3/2 pi and 2 pi. That's my start. Why there? Because cosine of 0 I know is 1. And cosine of pi on 2 I know is 0. Once I come out of cosine, I multiply by 2. 1 times 2, 0 times 2. Now, to get from row 1 to row 2, I would have had to divide by 3. So to move backwards, I have to multiply by 3. 0 times 3 is 0. That means that I do not have a phase shift right there. Multiply by 3, 3/2 pi. That means when I set up my chart, I'm going to count by 3/2 pi's. And this point, 3/2 pi 0, is what that one was. So we're going to set this guy up. Maybe down 2. Maybe we need to go up some more. We'll see. But my first point on there, I put in 0, I get out 2. My next point, I'm going to go to 3/2 pi. So I'm going to just start creating my tick marks. There's 3/2 pi. There's 6/2 pi. 9/2 pi. 12/2 pi. I need 4 increments to get my 4 translated, transformed, remaining good points. So my next point is at 3/2 pi. That's what my tick marks were. 0. Now, I need to understand there was no vertical shift. There's a plus 0 out here, which means I have just reached center line. So my next step has to take me in the same direction. I went over 1 increment, down 2, over 1 increment, down 2. Now I recover to sea level or center line, and now I have my up phase. So there's my cosine graph, just translated, transformed. My transformation of it. And I can build off of that if I so choose. Here's negative 3/2 pi, negative 3 pi. So my next step over here, down to here, and I could do this as much as you'd like to see. So there we go. So what do we learn? We learn our amplitude is 2 just based on inspection. I learned my center line was 0. So there was no vertical shift. Period. Right here. 6 pi. We learned all of these things. Horizontal shift. That first point was right here. No horizontal shift. Let's look at one that's more complicated and go through that process. Okay, cosecant. I'm going to graph this. I'm going to build my chart as if this was sine. Then I'm going to be careful not to graph the sine function. So what would we do? Choose x, multiply 3, add pi, and then we would take the sine at that point right here, big star, don't do it. We're not really graphing sine, but we're going to use it with its reciprocal. Multiply by 3, and then finally I would subtract 2. And I'm telling you, we only need 2 values, and we'll be able to answer all our questions and get our graph. We're going to know the period. We're going to know the domain. We're going to know the range, and we're going to draw the complete just on 2 levels of this stamp. The key is, when do I want to choose a value? What do I want to choose a value for? Not x, not 3x, but 3x plus pi. After I add pi, I want this to be 0. After I add pi, I want this to be pi on 2. I know the graph of sine from 0 to 2 pi looks like this. Therefore, sine of 0 is up 0, and sine of pi on 2 right here is up 1. Once I take sine, I multiply by 3, this times 3, and I subtract 2. 0 minus 2, negative 2, 3 minus 2, 1. Now I have to build back up the chart. Now watch this. If I take 3x plus pi and set that equal to 0, that gives me my horizontal shift. We talked about that on the previous page. What would I have to do? I would have to subtract pi and then divide 3. My horizontal shift is negative pi on 3. Well, look what we're doing here. To go backwards from here, I have to subtract pi and then divide 3. We're just solving the equation right here. So 0 minus pi, negative pi, divided by 3, or maybe you prefer times 1/3. We'd continue, but I'm going to hold off on that just for a second. You'll see why. Subtract pi, negative pi on 2. And now, when I multiply by 1/3, this becomes negative 1/3 pi, and that's fine if you want to use that. This becomes negative pi on 6. I kind of like to get common denominators in this step. So this is negative 1/3 pi, or negative 2/6 pi. I kind of like that. It helps in my counting. So let's see what we've got here. I've got a chart. I know I've got to go negatives for a while, so I'm going to, I don't know, maybe I got to go way positive too. But I'm going to put my line up here, and I'm going to go negative 1/6, negative 2/6. I think I'll go over to negative 3/6 pi, because conveniently that's negative pi on 2. Here's 1/6, 2/6, 3/6 pi on 2, and we'll see if that's enough for us. My y values, I don't know, I know I got to go down. Negative 1, negative 2, maybe a little further here. I'll add more as needed. My first point of my sine graph, which corresponds to this point, is at negative 2/6, negative 2. My next point is at negative pi on 6, positive 1. And this is where I have to distinguish between sine and cosine. Since I want to build cosecant off a sine, my sine graph I look at, this is this point translated. This is a center line point, but we already knew that. So you might even want to do a dotted center line. So my next point has to return to center line. That was my up phase. Now I need a down phase. Well, I went over 1 step, down 3. So I need to go over 1 step, down 3 to pi on 6. From here, down 3. And then I come back up. So right now, I would have, if I sketched it in, a full period of pi. And if it's just killing you and you got to sketch it in for the cosecant, do a dotted line. But our center line points determine our asymptotes, and our other points are our touches. Now, let's see. Period. Well, my period would be these 4 increments. That's 1/6, 2/6, 3/6, 4/6. The period is 2/3 pi. But you might remember what we said about period. Period is 2 pi for sine or cosecant divided by our x coefficient, 3. 2 pi divided by 3, 2/3 pi. Our amplitude, if we had an amplitude, which we don't for cosecant graph, but if it was a sine graph, our amplitude is determined by this, 3. We're up 3, down 3. Our amplitude would be 3. Our phase shift, right here, but look at this, we got it right there, is negative 2/6 pi. Our phase shift, our horizontal shift, I know we're not asking for all those things now, but our horizontal shift would be negative pi on 3. Set the argument equal to 0. We've got all of these things. So lots of information there. Our vertical shift, right here, down 2. Okay, now we're supposed to find the domain. Yikes. We got our period. We're going to find the range first. The range, this graph from negative infinity on up exists until we get to negative 5. from negative infinity to negative 5 and exists at negative 5. And then it starts again at 1 and continues to infinity. But the domain, that's a tricky one. The domain doesn't exist at 0, doesn't exist at 1/3 pi, wouldn't exist again at 2/3 pi, 3/3 pi, 4/3. It doesn't exist at increments of 1/3 pi. So I'm going to say x cannot equal plus or minus multiple 1/3 pi's, n on 3 pi's, where n is an integer. There's our domain. That one's a little bit sneaky compared to some of the things we've done. Okay, let's move on to some things we should be pretty strong at, I believe. Tangent of x equals 2.5. I need to get x alone. Therefore, x equals tangent inverse. I inverse tangent both sides. I don't like 2/5 or 2.5 because what goes into inverse function should be a ratio. I could put 2.5 on 1, but I could also put 5 on 2. And I immediately recognize that that value, this is not a good triangle. It's not a 30, 60, 90. It's not a 45, 45. And then I still want to get a picture of it. So 5/2 is our tangent ratio, which is opposite on adjacent, or y on x. And tangent is positive. We could do this, and I expect everybody will, and I do too. All positive students take tangents positive here, take calculus. So we know we're here and here, but another way to do it is to say, well, when is y on x positive? When x is positive and y is positive? Or when x is negative and y is negative? I'm going to draw this sort of to scale so we'll know whether to believe our answer or not. Long y 5, short x 2. Long y negative 5, short x negative 2. So I mentioned earlier, if tangent inverse was if the problem started right here, there'd only be one answer. But this says what values of tangent, or what angle can we put in tangent to get these? When we invoke tangent inverse, now we can have multiple answers, and clearly we should have 2 here. So I'm going to go on to my calculator. You can do this at home. I'm going to make sure my mode, they're begging me here to be in radians with this. Make sure I'm in radians. I'm going to get back out of there. I'm going to go second tangent inverse, and I'm going to go either 2.5 or 5/2. And it gives me x equals, I'm going to round to 2 decimal places, 1.19. So should probably say approximately equal to. Now, 1.19, if we're not really ingrained in radians, maybe we don't catch this. That's this angle measure. Now, if I went all the way to here, that would be pi on 2 or 1.57. So less than 1.57 and closer to 1.57 than 0 makes sense to me. So we have that answer, but we also have an answer where we go all the way around to here and now up to here. We can't go backwards because they say we can only go from 0 to 2 pi. So this answer would be pi 3.14 plus, this is clearly equal to this, congruent triangles, another 1.19, so we get 4.33 for this second answer over here. Okay. All right, cosecant. Our calculators don't even have a cosecant inverse button, so I'm going to change this to sine of x equals 1/2, the reciprocal functions. Therefore, x is sine inverse of 1/2. Well, that is the sine ratio. SOHCAHTOA land, I'm not trying to draw this one to scale yet. That's opposite on adjacent, or we want to know when y on r is 1/2. I do recognize that as a 30, 60, 90, and the y is the small side. My sides are 1, root 3, and 2. I could, all students take calculus, signs are positive here, or I could say sine is positive when y on r is positive, and that only happens when y is positive. When is y positive? Up here and up here. When is it the short side? When we have 1, 2, and a root 3, or when we have 1, 2, and negative root 3. So these I recognize as 30-degree angles in here. and that is 1/6 pi. Again, we're in radian measures, not degrees. And 1, 2, 3, 4, 5/6 pi, or 1/6 pi short of pi. Okay, very similar. However, we're looking for solutions all times that sine hits -1/2. And think about this. Here's our sine graph, but it goes on and on and on forever. When does it hit -1/2? An infinite number of times. So we have some naming challenges with all the time that gets down to -1/2. But I'm first going to go sine of x equals -1/2. So I can go sine inverse, or x equals sine inverse of -1/2. Well, once again, -1/2 is our y to r ratio. And r is always positive, so y has to be negative. -1 to 2, and -1 to 2. Now, since I have all answers, I'm not limited to going forward or backward. I may choose just to get to this angle by going backwards, pi on 6. And I may choose to get to this answer over here by spinning around 5/6 pi. But I could also get to this by going backwards, pi on 6, and spinning 6 times around the circle, or 20 times around the circle. So I need to add multiple revolutions, the revolution being 2 pi and n being the multiple, plus multiple revolutions where n is an integer. Okay, hope that helps. That is the end of the first chapter. We're going to be in review mode for a bit, and we will be seeing some problems that are perhaps a little bit more challenging than the last couple. I think these are a fairly good challenge, but we'll be talking about that over the next couple of days of class. Thanks for tuning in.